start again. We already know a lot. We know what is topology. And now we'll try to use this knowledge to define even more notions and give even more examples of topological spaces. So, first of all, if we have a space, topological space X, it's a topological space. It is a natural source of many other topological spaces, which we can construct from its subsets. Okay, so for such a topological space, we can define a topological subspace, okay, of this space. And how we do that? Let's say that S is a subset of X, okay, it's a subset, and we define topology on S. We define topology on S in the following way. Let's say U is open in S. Okay. If there is open V in X, such that U is S intersected with V. Okay? Is it clear? Okay. So we take a subset S of the big space X, and we define mu topology not in the big space but in the small space. Right? You can draw a picture. Let's assume that's X, and let this part be S. Okay? Like a subspace. And we say that a set here, maybe like this. Okay? This set is open if there is another set like that, such that this green one is the intersection of this red one with the blue one. Here. Okay. So in this picture you see that the green set is open in the blue set because it's the intersection of the open set in X and a set S. Okay. It's basically what it says here, what is said here. And this space S now, this space, together with this topology, which we call inherited, because this topology on S is inherited from X, it's a topological subspace.
Excuse me, do we have to assume that S is an open set in X?
No, you don't have to.
Okay, fine.
So, in this way, having one topological space, you can generate many other topological spaces as these subspaces, yeah? Of
In
X.
Polish this odziedziczona?
Tak.
Yes.
And what is important and interesting from a philosophical point of view, it is that it can happen that some sets are open in one space, but are not open in the other space. Okay? So it's a kind of relativity that enters into the game. Yeah? That we see that this openness is relative to the universe that we take into consideration. Okay? So, for example, let's think about a disk. Okay. We have a disk. And this disk is our subspace of a big space which is a Euclidean two-dimensional space, right? This is X, this is X, and this is a disk S. And let's say that in this big space we have we halve the big space into two areas, right? And now consider this area. Okay, this red one. The question is, if the red area is open or not. How do you think? This? It is not open. Why not?
I think it's running by S.
Oh yeah, it's bounded somehow by this S. So for example, if I understand correctly, there is a point here, right? There is a point here, and this point is on the boundary. So if we paint even a small ball around it, then we will go outside of the set, right? So here the set is here, and even a small ball takes us out of the set, which means that this set is not open in X. Okay, so let's call it call it Z. So Z is not open in X, but Z is open in S. Why is that? Because Z is an intersection of S and an open set, this green one, let's call it Y. Okay? Because if you intersect the green one, which is open, with S, you will get precisely this set. Which means that it fulfills this definition. And you can also see it in this way, that from the perspective of S, it doesn't matter that this point is on the boundary, because in fact it's the end of S. So there is nothing more outside of S. There is nothing more. We see that there is something more because we are looking at the whole space, the whole universe X. But from the perspective of S, it's the end of the world, right? This is where the world ends. And where there is a continuation, so it's here, this set is open, yeah? Because here it is open. So from the perspective of S, this is not the boundary. We perceive it as a boundary because we are looking at the big space X. But from the perspective of S, the only part of Z which is boundary, it is this part. Okay? Is it clear? Okay. Yeah? Questions? All right. And we say, in this situation, we say that this set is relatively open. Okay? So it's relatively open in relation to a given subspace. Okay, maybe we can skip this. Ah yeah, there was one thing that I didn't say, and I should say it now, which is it's just a terminological remark, but it's important. Morphisms in the category top, so topological spaces, okay, are called homeomorphisms. So topologists have their own word for morphisms. Okay?
You should say
Isomorphisms. Isomorphisms. Yeah, excuse me. Isomorphisms. Topologicians have their own word for isomorphisms, and they call it homeomorphisms. Okay? Okay. But that's just, as I said, that's just a vocabulary remark. And now another definition, that if we have let's say how to put it, definition, another definition. Okay? Definition. Let's say we have S as a subspace of Y, okay? And we have how to put that? So let's say we have a map here. Let E be a map from S, Y. Map. If S and the image of S in Y are homeomorphic, which means in a certain sense isomorphic, okay? So they are the same from the perspective of topology, then we call E an embedding. Which in Polish is zanurzenie.
Czy to jest endomorfizm?
Czy to jest endomorfizm? Tak. Okay, and now an example. An example, let's say. Actually, we can even skip this. We can even skip this. It's not necessary. You don't have to put this. It can be like that, but it doesn't have to be like that. Okay, so now in this situation, let's give some examples. So let's say we have an interval. And we have a space. Two-dimensional space. So we can think about this interval as this interval, yeah? And if it's the same interval, then we have that S is a subset of Y, okay? This is Y, this is S, in this definition. So if this interval is this one, then it's a subset. But it can be from somewhere else, taken from somewhere else, and try to embed this one here. Okay, we can try to embed it here. And for example, we can try to put this interval here. Okay? We can try to find a function that takes this interval into this subset of the space Y. Or if we consider that this interval is this one, we can just think about it as an internal endomorphic transformation of the space Y. And how we do that? For example, we can define that the function f from the point t, this point t belongs to this interval 0, 1, right? This is t. And we can define that this is 1 minus t times a plus t times b. Okay, we can define such a function. And we can easily see that if t is 0, for example, then we have 1 minus 0 is 1, so it's 1 times a plus 0 times b, which is a. So it shows us that 0 goes to a, and just to check the other end of the interval, if we put 1 instead of t, we will have 1 minus 1, which is 0. 0 times a is 0, plus 1 times b, which shows us that 1 is being taken to point b. So that's just an example how you can embed an interval into a space. So in other words, you can take a space and embed it into another space. Yeah. And also note that this is a continuous function. Okay, is it clear? That's just an example. There is no theory behind, just to show how it works. Okay, can I go through that? So now another word which will be useful, I guess, tomorrow and the day after tomorrow. We would like to define what is an interior of a set. Okay, interior of a set. So let's say that definition, okay? So let A be a set in X and define A. There are different symbols saying that it is an interior, but that's one of those that are being used. That's this 0 here. Okay, and we define it as the sum of all B such that B is a subset of A and B is open. This is interior of A. So what it means, you can see it in the picture. Let's say if this is A, and now we take all the subsets of A, because these are subsets of A, which are open. Okay? So what are the open subsets? This one, 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 all these subsets. We take all these subsets, we sum, big sum, probably infinite sum of those. And what we get like a big subset. It's still a subset because all of those components are inside of A, so the sum is still inside of A, right? Yeah, is it clear? If we add things which are inside of A, we cannot go beyond A. We will still be within the boundaries of A. And on the other hand, we know from the definition of topology that if we add even infinite number of sets which are open, we will still get a set which is open. Okay? So the sum of all those sets which are open is still open. So this set is open, and what else is the biggest open subset of A, biggest possible. And that's the intuition behind interior. So if you have an object in the space, we can think about it, we can consider its interior as the sum of all open subsets of this object, which somehow fill this object from inside. Okay? So it's being filled from inside with those open sets. So for example, let's say we have an interval from C to D on a real line. Okay? A closed interval. Can you say what is the interior of this interval?
From C to what?
D. It's D.
Okay, so it's from C to D without C and D.
Perfect. Yeah. So this is the interior. Okay. So it's the biggest open subset of the interval from C to D. It's the open interval from C to D.
Is it the only possibility here? Because there is smaller and equal, so would it be like a part of that also called like the interior? Because this is like the biggest interior that can be here. So like if we draw something smaller here, it would still fit, I think, the definition of that. Yes, am I right?
You know, if the set A is open itself,
yes,
then B can be equal A.
but it can be smaller as well. Like from
Yeah, but
so
it
it
doesn't.
doesn't have to be this one, but it can be something like much smaller here. Yes?
No, but you sum all of them. You sum all of them. So if among these elements that you sum, you have the whole set because it's open, then it will be equal A. So, in other words, if A is open, then A equals the interior of A. Okay? Because you take A as one of the components of this big sum.
Oh.
Yeah? And if you take A, then you don't have to count anything else because A is the biggest one.
So A has to be taken here as the component as well.
If it's open. If it's open.
Does it really indicate this B is smaller than equal A?
It's not. It doesn't indicate that, but
Okay, maybe it's stupid, but this B smaller or equal than A,
yeah.
does it indicate that there has to be this A as well? Because it's not equal.
No, because you have two conditions. Because it's not only you don't only count B's that are smaller or equal to A, but you count B's which fulfill two conditions at the same time. First, they are subsets of A, and secondly, they have to be open.
So they have to be taken simultaneously.
Okay. So that's how you can think about interiority or interior part of a given set or subset or anything. And also another definition. My workshop is based on definitions, as I said at the beginning. So I will give you many words that you will be able to use and apply later. Yeah. There will be no big theory in what I'm saying, but that's my task, yeah? To give you the vocabulary. Okay, so let's say let F be a set in X. Okay, we call F closed if X minus F is open. Okay. So it's a kind of duality. So whenever you have an open set, it also defines a closed set. If you have X, and if you have open set here, the rest of the space is closed. But that's just a definition, yeah? There is nothing, not much behind it. It's just how we call objects. Yeah? We call such objects are being called closed. And of course, it is a kind of duality between openness and closeness. Yeah? One of them is the counterpart of the other. But it's not like that, that if a set is not open, if, let's say, if O is not open, it doesn't mean that O is closed. Okay? It's not like that. There are sets which are neither open nor closed. Yeah? Can you give an example? Empty set actually is both open and closed. Why is that? Because if you have open set, from the definition of topology, it's open. But what is X minus empty set? It's X. But X also from the definition of topology is open. So if X is open, then it means that empty set is closed. Right? So it's both open and closed.
Are there any other examples of both closed and open sets?
Yeah, for example, X also is open and closed at the same time, independently of the topology, because it's in every topology it's like that. But there are also more sophisticated examples. I will give it in a moment, but just please give me an example of a set which is closed and open at the same time. Excuse me, no, which is not open and not closed at the same time. Neither open nor closed. Yeah, we can think about, for example, let's consider a real line, and let's consider an interval which is closed from one side and is open from the other side. Then it's neither open nor closed. And why is that? Because you can argue in different ways, but let's say in this interval you have a point which is on the boundary. So you can, even smallest ball, even smallest disk around this point will go outside of the set, right? So which means that it's not open. Yeah, so it's already written here. So if this, because of this point, it's not open, because you cannot embed a small ball around this point that will be inside of the set. But on the other hand, if you look And the set which is outside the complementary set here, there is another point here. Yeah? And this point, looking from the perspective of green set, right? If you put a small ball around this point, even the smallest ball, you will go inside of this red set, which means that the green set is not open. And if green set is not open, it means that red is not closed. Because closed is a set which counterpart is open. Is it clear? Or please tell me, because I don't know if it's clear or not to you.
Could you repeat why is the green one closed?
The green is not closed. Yeah? Yeah, okay, so I can say like green is not closed. Green is not closed. Why? Because, maybe I'll write it, yeah. So, what would that mean that green is closed? That green, let's put it like that. Green would be closed, right? If R minus green, right, would be open, right? That's the definition. That's not a theorem, it's not a fact, it's just a definition, poor definition. So it means that we have to consider if this one is open, right? And it means, and this one, R minus green, is red actually, okay? So we have to check if red is open. And is red set open? No. Why? Because, let's call this point, let's say C, okay? Because let's put it like that. C is on the boundary of the red set and is an element of red set. So it means that every ball around this point goes beyond the red set. Yeah? And we said that if a set is open around every point in this set, a ball around every point in this set, not every ball, but there is a small ball around the point in this set that is inside of the set. Yeah? So if we have a set which is open and we have a point in it, then we are always able to find a small disk around this point, such that this point together with this disk is inside of the set. If that does not happen, then it means that the set is not open. Okay? Is it clear or not? Or maybe another question: where it is not clear? At which point this is not clear? This reason.
Well, I might make a confession.
Yeah.
Yes. for me it's not clear, and it's not clear because it's too abstract. I mean, you said you are giving to us vocabulary, and I cannot imagine a meaningful sentence I can make out of this vocabulary, to use this metaphor, yes? I'm still thinking about possible philosophical applications, yes, and well, it may be the weakness of my philosophical thinking or imaginary, but for example, just to give me motivation to follow the lecture. Is it, how do you think, is it possible to use this topological vocabulary to elaborate an account of, for example, supernaturalism, supernatural metaphysics? You know, this. I think this philosophy is one of the most important, I think, issues now. The kind of discussion between naturalists and supernaturalists. Yes. Do you think it would be possible to make an account of this problem, of this discussion in terms of topology?
That would be difficult to apply it now, just like that. But I can say, I can give you maybe another example, another exemplification. Maybe you can think about this open sets in terms of something which is not precise. Okay? Something which is vague, yeah? Somehow. I mean, for example, if you have such an open set, you think about something that has a known boundary. So, for example, like when you're on the border between two countries.
Okay, so may I stop?
Yes.
Because I think perhaps vaguely, but I grasp the idea of open, this open closed set. This is not a problem for me. You said in the beginning that it is kind of language, yes?
Yeah.
And the importance or value of this language is that it is useful or can be useful. What is the use of this? I mean, in terms of philosophy, where I can apply these concepts, yes, of open.
I would say, yeah, that's.
And for example, if you could point to the metaphysical problem, but in traditional metaphysics, in which you could apply these concepts.
I think that the whole Mariology is about it, yeah? How to apply this apparatus, this topological apparatus to ontological problems. And I guess you will get plenty of examples tomorrow and the day after tomorrow, etc., etc. But these are rather complicated, complex issues, and I don't feel like I'm able to explain it just like that now.
Okay.
Yeah? I can say that if you consider, for example, if you want to talk about, I don't know, ontological problems of objects which are not, because for example, you can have an ontological problem where an object starts and where is its limit. Yeah? So for example, a human being, where is the limit of a human being? Is it precisely defined or not? For example, if, I don't know, thinking in a biological way, you can think where is precisely the point where a human being ends. And you can use a microscope and you can see that these are those tiny cells on the border of a human being, and some of them are, for example, already dead, like our cells of our skin, which are already dead. Are they a part of us or not? And you can try to ponder this issue and try to define where is the border of the entity of a human being. And somehow you can try to use this vocabulary of open and closed sets. You can try to say that some objects in the ontological space are roughly or are sharp, and you can precisely define where they start, where they end. And in case of some objects, you cannot say that. You cannot pinpoint the boundary. Yeah, so in this sense, discussing the boundaries and trying to define it in a precise way, what is an interior? For example, what is the interior of human being? You can try to use this vocabulary to speak about these things in a more precise way. Yeah. And you can then try after, yeah, as I said, that topologicians are often doing this, it in the following way, that they define problem in topological terms, then they use algebra, then they solve the problem, and then they interpret it back in topological terms. So you could try to do the same trick with philosophy. So you can take an ontological problem, interpret it in the language of topology, then use the topological apparatus to solve the question, for example, and then interpret it back to the language of ontology, for example. So that's the basic idea, I would say, yeah?
I was wondering, going back to what you said at the start about, so you mentioned about topology being a language to be able to describe rightly. If a set which is neither open or closed is not in a topology and it's not the complement of a set. So could we say that this is something for which our topology doesn't give us a word?
Yeah, somehow. It says something about this object. For example, that it's not measurable from the perspective of this topology. It's not a big knowledge, but it says something. That, for example, it says that it's strange in our world. Mm-hmm. Yeah, somehow. But for example, if you imagine this very poor topology, this topology where you have only empty set and the whole space and nothing else, then this topology don't tell you much about your world, yeah, because it can only say that an object is empty, or is everything, or is something not empty and not everything, yeah, which is a very basic knowledge, but it says something, yeah. And you can also try to apply much richer topology that will enable you to differentiate objects with a bigger subtlety. Okay. Well, any other questions? Philosophical questions, not only mathematical questions. Because from my perspective, what is most important is not. I think that it's not necessary that you understand the whole technical apparatus behind these things. You don't need to understand everything in technical sense. But I would love if you could get the intuition behind it, yeah? So you don't need to solve topological exercises and count what is the sum or intersection of some sets, etc., etc. But if you grasp the very idea of this vague boundary, or what is the difference between being closed and being open, or if you grasp the idea of being able to say something about an object, that it belongs to the topology or it doesn't belong to the topology, or if you grasp the idea that some objects can be similar from the perspective of topology, homeomorphic, isomorphic, and some are not. That is, I would say, valuable. But excuse me, you had a question. Yeah.
No, just perhaps an example where you can see the usefulness of topological language. Open subsets may be considered as reasonable experiments. So if you variate a little bit, then the results of the experiments are still the same. You can tottering about a bit, but if you make experiments on the boundary of an open set, so to speak, the results are unstable. Very little variation sends you to the negation of a hypothesis, and a very small negation puts you on a confirmation. So you can, via topological means, offer a useful explanation of reasonable confirmations and falsification.
Yeah, you're right.
I mean, this is sort of philosophical application.
But don't you think that this boundary is too thin for confirmation of hypothesis? I think that physiology could be better, because here this boundary is infinitely tiny, and in real life the sphere of experiments and situations in which hypotheses are tested is the margin is wider, I think. So
if I may answer, don't be misled by the fact that in this picture it looks tiny, because in in mathematics, let's say in topology, you can find many sets which consist only from the boundary. So, for example, whole sets which are only boundaries, so sets which are equal to its boundary, for example, yeah? And there are huge sets which are boundary itself.
Rational numbers, for example. Consider the example of rational numbers as a subspace of real numbers.
If we have, that's one of the examples. If you have real numbers, but you can even say, even give better example, because irrational numbers have the same feature.
This amounts to the same.
Yeah, but there are uncountable many irrational numbers, and that in this sense it's more. So if you look at the irrational numbers on the real line, this is the set that fills almost everything in the real line, and it is equal to its boundary. So the whole set is a boundary. There are only countably many elements from the real line which are not in this set, and the whole set is a boundary.
There are countably many which are in.
Excuse me?
There are countably many which are in the set, and uncountably. About which set you are talking?
I'm saying about irrational
okay,
numbers.
sorry.
Yeah, irrational numbers.
But then you should define what the boundary is.
Yeah, I know I should, but I would avoid that because that's technically complicated. So, actually, I will define what is a boundary, but not. Well, maybe I should say that. No, but I need one more notion before we do that. Yeah.
Excuse me, there's also, I think, kind of a spatial intuition in the case of open sets on the, for example, Euclidean plane as ones that when you are inside, you cannot go outside the set a finite number of steps, for example. You know? So it is like if you are moving towards the boundary, you will never reach this boundary, something like that. You could use it as a kind of a spatial intuition. And if you, on the other hand, if you close it, it can be treated as a counterpart of a finite region in space, or something like that. You know, finite in the sense that you can just walk through this, and this is what can give some insights in relation of this to nature of space, for example, or something like that.
Yeah.
But this is of course a metaphor, and then
Yeah. It is a metaphor. Yeah. But I don't know. Also, I prefer to use metaphors because trying to speak about those issues only in technical topological way makes it even more difficult. All right. Yeah, so maybe if we want to... you have any questions?
Why is the neither open nor closed?
Ah, yeah, okay, get back to the question. Okay, so, yeah. The intuition is, as I said, just please answer. If this intuition is clear, that if this reasoning is clear, that if you have an open set, for every point in this set, you can find a small ball that will fit into the set together with this point. Is it clear? Okay. So now, if you look at this red set, you can indicate a point, this one, this red here, which does not fit into the red set with any ball around it. It fits itself, but if you put even the smallest ball around it, then it doesn't fit, right? And the same is true about the green set, which is also not open, because there is this point in this set, this green one, and this green point is an element of the green set, but even the smallest ball around this green point goes outside of the green set, right? Because if you this green set looks like that, yeah. So it's like sharp ending, right? So this set is not open, and this set is neither open. And we define a closed set. We define a closed set as a set which has an open counterpart. Right? So if it's not open, then this one is not closed. Okay? Because green is not open, red is not closed. Is it clear? Oh, great. All right. So now maybe because we would like to define this boundary, so we need to define what is the closure of a set, and let's define it like that. Because we have this definition of an interior, yeah, this is the definition of an interior, and we have like a dual definition of a closure of a set. So let A be a set in X, and we define a closure of A in the following way. Okay, and that's closure. And how we understand that? This sign, you see, this is like a similar sign to this one, which signifies intersection. Yeah. So, as in this picture, we took all the sets which were inside of A. Here we take all the sets which are bigger than A, okay? So we have the set A, and we take sets which are bigger than A and are closed. For example, this one, or this one, or this one. Okay, so all these sets are bigger than A, and we take intersection of all of them. So a common part of all these bigger sets. And what happens? We get something that bounds A from outside, but bounds it very tightly. So it's like around A. It's the intersection of all sets which are around A, which is like here. So let's say that's the intersection. And this set is closed because it's an intersection of closed sets. Okay. So, do you have any questions? It's like a similar object, but here you feel a set from inside, and here you try to bound it from outside. So, for example, if you have a set like this, okay, this is a set. This is a set in a real two-dimensional space. Okay, and what is its interior? How you would draw its interior? Interior is like taking everything which is open in this set. So you see that it has these two sides which are already open, but it also has two sides which are closed somehow, metaphorically saying. So an interior of this set would be something like this. Okay? It's full inside. Yeah? And what would be the exterior? What would be the closure of this set? The closure of the set is a kind of a dual concept, which means that everywhere where it is open, it becomes closed. Okay? So a closure of this set would be something like this. Does it make sense? Do you feel the difference?
In fact, not really, because I was also thinking about those two definitions and sets which has and hasn't the boundaries. So, like, what would be the difference if you draw the square having those two boundaries which aren't bounded, and those two which made it the other way around? What would be the difference between interior and closure?
No difference.
Exactly. So the question about boundaries. So it doesn't really, for me, explicitly. It comes out of those two definitions of the closure and I mean the first one and the second one. So
I didn't give the definition. I haven't given the definition of boundary yet. I will define it soon.
Because here I don't see the very point would intersect those two. So this one is right here, but I mean I don't get it really here.
So I will speak about boundary in a moment, but what I wanted to say now is what is an interior and what is a closure.
Yeah, so this I understand, but exactly this one, what you draw, so equal and then it's different.
Yeah, these sets are different, but they have the same interior and the same closure. Okay?
So what about the boundaries?
And the boundary, actually, we can define the boundary of a set. So the boundary of A, we can define as the closure minus the interior.
I mean, I know that, but I mean, it's quite.
But I haven't said it yet.
I mean, logic, but then how would you define the difference between, let's call it 1 and let's call it 2?
They have the same boundary. They have the same boundary. So the boundary in this situation is the following object. That's the boundary, without anything inside. Yeah? That's the boundary. Like a limit. If you look at the map, for example, geographical map of Europe, you can see countries, and there are like interiors of countries, there are exteriors of countries, and there are borders.